In this particular lesson, we're going to talk about two things. The major one is going to be on significant figure arithmetic, how to add, subtract, multiply, and divide numbers that have a set number of significant figures so that the answer has the correct number of significant figures afterwards. It doesn't mislead us about the precision of our result. And the second thing is sort of a brief talking about miscellaneous significant figure rules, both in general and for the ones we'll use in our particular class. So first is going to be on multiplication and division. The rule for conserving significant figures whenever you multiply two numbers together or divide them is this. As it says on screen, when multiplying or dividing any two numbers, the result will always have the same number of significant figures as the original number with the fewest significant figures. So if I am multiplying two numbers, one which has two significant figures, the other which has three significant figures, then the answer will have two significant figures because of the fact that of the first two significant figures and three significant figures, the one that had the fewest was the one that had two. So we have some various problems with their unrounded and rounded answers at the bottom. Taking a look at the first one here, we have 17.1 times 8. And so if you do that in your calculator, you'll end up getting 136.8 as your result. Now, let's take a look at the number of significant figures in our first two numbers here. 17.1. Well, it has three non-zero digits, so that means it is going to have three significant figures. Our next one, times 8. 8 only has one significant figure, so which one is going to be the fewest? Well, the one that's the fewest, 1 is smaller than 3, so it'll be 1. That means our answer is only going to have one significant figure, so it's going to be just this one right here. The 3 does not, 3 will round down, and so we get a rounded answer of 100 right there. Alright? Taking a look at our next one, 0.0034 times 131.2. Put that in the calculator and you get 0.44608. Taking a look at our first two here, we only see that there are two significant figures in the first one, 3 and 4. Gives us two significant figures. For the second one, 131.2, that has four significant figures, 1, 3, 1, and 2. Of those, which one is smaller? The 2 is. So we're going to round our answer to two significant figures. That will be 4 and 4 here. The 6 afterwards rounds the last 4 up to 5, and so we get 0.45. So that's what we get right there. Next one, 671 divided by 0.30. 671 has how many significant figures? 3. 0.30. The 3 is significant. The last 0 is a trailing 0 on the right, to the right of the decimal, so it is significant. So that will have two significant figures. The smaller one there is 2. So our answer is only going to have two significant figures, so it'll be this one and this one right there. And so that's going to round to 22,000 because of the fact the 3 rounds down. Okay? On our next one, 8 times 10 to the 8th. Well, that only has one significant figure. 1.2 times 10 to the 4th has 2, so that means that we're going to only have one significant figure here. So we're going to round our answer, our unrounded answer, 6.6666667 times 10 to the 4th. We'll only round to the first one here. Since the next digit is a 6 there, that's going to round up, so we get 7 times 10 to the 4th. Our last one, 500 divided by 2. Well, that's the one you do in your head. It's 250 for the unrounded answer, but 500 only has one significant figure. 2 only has one significant figure. So the fact is, which one is the least? Well, they both are. Both are going to be the least number right there. Neither one really affects things. Or they both affect it to the same level. So if I wanted to round 250 to one significant figure, that would be just this guy right here. Well, then the 5 is going to round up, and so that's going to give us an answer of 300 right there. So that's going to be our rounded answer. That looks like that wouldn't make much sense, but if you think about it, it does, because of the fact that if I say I have 500 to one significant figure, then what that means is this could be anything from 450 all the way up to 550. And if I write down that I have 2 here, that could be anything from 1.5 to 2.5. And so you could imagine a case where if you were going to take 450 divided by 2.5, that's going to give you a number that's going to be a whole lot less than 250. Sorry about that. It wouldn't give you anything that's anywhere close to 250. And so to make sure our rounded answer is correct, then we have 300. That's the one that has the correct number of significant figures. Addition and subtraction is a little more complex. It's a little less intuitive than it is for multiplication and division, but it works very similarly. The rule is this. When adding or subtracting any two numbers, the result will be rounded to the rightmost position or place of the original number that is the least precise. So, for example, if I had a number like 13.1, the rightmost digit in there is like the 0.1. That's in the tenths place. And so the rightmost position would be the tenths place for that one. If I had 130, for that number right there, that last zero is not significant because it trails bits on the left side of the decimal. So the last significant place in 130 is the 3. That's in the tens place. So taking a look at what we do here, let's look at some examples. We have a problem, 17.1 plus 8. When we add those together, we get 25.1. Looking at our two original numbers, the two places that are the rightmost places are, for the first one, for the 17.1, what we have there, that's going to be the tenths place. So that's going to be the tenths. So that's the 0.1's place. For the 8, the rightmost place is the ones place. So the which one of these is the least precise? Well, the 17.1 is rounded all the way to the tenths place. That's fairly precise. The 8's rounded only to the ones place. That's not as precise. So the one that's the least precise is going to be the one that's rounded to the ones place. And so we want to round this 25.1 to the ones place. And so the ones place is right there. And so we're going to scratch out anything that's basically after that. And so we end up with a rounded answer, which is 25. Okay? For our next one here is that if we take a look at this first one, 0.0034 minus 131.2, we do the math, we get negative 131.1966. 0.0034, that's rounded to the, let's see here, we have tenths, hundredths, thousandths, 10,000ths place. The rightmost place is going to be in the 10,000ths. So 1 over 10,000ths place. Okay? It's a little hard. So on our next one here, 131.2, this one, the last place is the tenths place right there. So this one right here is going to be to the tenths place. Which one of these is going to be the least precise? Well, 1/10, if you measure it to the nearest 1/10, that's not less precise than measuring to the nearest 10,000ths. So we're going to go to the tenths place. The tenths place is going to be right there. It's going to be the 0.1. The 9 that goes after it is going to make it round up. So we're going to end up with negative 131.2 as our final answer there. Okay? Our next one, 671.0 plus 0.30. We add these two up, we get 671.30. Now in this case, let's take a look at the first digit here. 671.0, the rightmost significant place is going to be the tenths place. For the 0.30, the rightmost place is the hundredths place. So we have tenths versus 100ths. Which one is less precise? 1/10 is less precise. So we're going to round this to the tenths place right here. So the tenths place means 671.3. The 0 gets dropped off. Next one, 8 times 10 to the 8th plus 1.2 times 10 to the 4th. This one we have to look at a little differently because these are scientific notation. Right now is that we have the smallest place on this first one. It's where this 8 is. That's in what place? Well, it's in the 10 to the 8th place. Because it is 8 times 10 to the 8th is the thing that's basically just the left of the decimal is multiplied times 10 to the 8th power. Our next one, our smallest place, is 1.2. Well, since the 1 in the 1.2 is the 10 to the 4th place, it means the 2 must be in the 10 to the 3rd place. You always sort of take it down 1. And so from that right there, we are comparing which one is less precise, 10 to the 8th or 10 to the 3rd. Well, 10 to the 8th is a bigger number. It's going to be less precise if you measured it to that. And so we're going to take it to the 10 to the 8th place. And so in this 8.00012 times 10 to the 8th, the 10 to the 8th place is going to be this spot right here. And so it just becomes 8 times 10 to the 8th for our final answer. Our final one that we have here is 500 minus 2. That's just 498. The 500 is rounded to what spot? Well, the last two zeros aren't significant because they're trailing and they're to the left of the decimal. So our last significant place is going to be the hundreds place. And for the 2, the last place, there's only one place it's got. It's going to be the ones place. Which one is less precise? The hundredths place is less precise than the ones place. So we're going to go about and round that to the hundreds place. Hundreds place is right here. 498 rounded to the nearest hundred is going to be 500. Now I want you to take a look at this. in this particular case is that what number do we start off with? 500 minus 2? Our answer is 500. That seems like that wouldn't make much sense, but it's no different than the analogy we talked about in the previous lesson, is that if you say that something's a mile away and then you step back an inch, would you still say it's a mile away? Yes, you would, because the fact is that an inch is so much smaller that it's below the smallest significant digit for the miles that you gave before. So this is what you get here. 500 minus 2 is 500 if you're talking about the correct number of significant figures. We have a few miscellaneous rules. The first two rules are these that are rules that are always true, and that is that exact values have infinite significant figures. And so if something is exactly 2, then you don't say it only has one significant figure. It doesn't have 3. It has an infinite number. It's 2.000, and you can keep saying zeros for the rest of the universe's life. Examples of this are mathematical constants like pi. If you write down that pi times something, that's considered to be exact. Now, oftentimes when we're multiplying things, we actually will round it. Well, obviously we round it. We put 3.14, not 3.1415, etc. So actual mathematical constants have infinite significant figures. Defined unit conversions also have infinite significant figures. How many inches are there in a foot? 12 inches in a foot. Is that 12 inches the nearest inch? No, it's exactly 12 inches. It's 12.00000 forever. It's because the foot is defined as being 12 inches. That's just the way that things are here. Same thing is true for a number of other things, like how many centimeters are in a meter. Well, a centimeter is defined as being 1/100th of a meter. So is it 100 to the nearest centimeter? No, it's exactly 100. It has infinite significant figures. These next three rules are what we're going to call house rules. These are things that are going to be true for this class, but in chemistry, but aren't necessarily always true outside of class. In fact, this first one is one that isn't true outside of class, but we're going to assume it is just to keep things simple for the purposes of the class. And that is that physical constants, such as atomic masses, the mass of an electron, things along those lines, are considered to be exact. So if you look on your periodic table when we get to that, and it says that the atomic mass of hydrogen is 1.01. Normally that would have 3 significant figures, but for any calculation that we do, we're going to assume it's exact. So it's 1.010000 forever. Another one would be given unit conversions. We said before that unit conversions that are defined, like a foot is defined as being 12 inches, we'll say it is exact, has to be infinite significant figures. We're going to say that any unit conversion that I give you is going to be one that we consider to be exact. An example would be 2.54 centimeters in an inch. That's the number of centimeters per inch. Is it exactly 2.54? No, it's not. That is rounded to the hundredths place. But we're going to treat it for this class that unit conversions are going to be given infinite significant figures. And then the last one for our house rules is it spelled out numbers. So if I say that something is doubled, do you multiply it times 2 and that has one significant figure? No. Doubled is a word. We're going to say that's exact. It's exactly 2. If I say that it's times, said 14 is the example that I give here. If it spells it out, then consider it to be exactly 14. If it says 1/3, consider it to be exactly 1/3, and so on and so forth. The reason why this is important is that if you have a value with infinite significant figures, then they don't affect the final rounded value. And so if I said pi times 3, for example, so you multiply those two together, is that the number of significant figures in pi, you don't worry about it. You only worry about the number of significant figures in 3, or 7 plus, the atomic mass of boron, and so you do 7 plus 6.91. And so which one is going to affect it? We don't worry about the atomic mass of boron because for this class that's a physical constant. It's considered to have infinite significant figures. You only worry about the 7 that you added up, or the 6 you added up before. So so that's the reason why this is important. Just keep these in mind for the purpose of this class, and keep the miscellaneous, the exact value rules are going to be generally true for significant figures there.